This is a nice paper that actually is my favorite topic as well. It talks about a climate change signal in the tropical Pacific that's emerging from decadal variability. This issue I've talked about in the monsoon variability as well. People take a long time series, draw a linear trend and say there is a trend, but often decadal variability can be confounded with the trend. It's tricky because how long does a trend have to last for it to be separate from decadal variability, or can it be called a secular trend? And of course, the trickiest thing is that the global warming, climate change itself can also modulate decadal variability, and a 20-year cycle may become a 30-year cycle. So these are tricky things. But Richard Seeger and Mark Kane, they have been obsessed with this tropical Pacific response to anthropogenic forcing, and I've been involved in a few papers with them from the time I was still, very young. The Eastern, let's read. It's a nice long paper. I'm going to show all the figures but not read all the text. It's really worth reading if this is of interest to you. And obviously I will be brief and pick the most salient points according to me, but we'll read the discussion, which has a nice summary of what the paper is all about. Okay. So I still have a kind of a stuffed up breathing system that doesn't seem to go away. The Eastern Tropical Pacific, just giving you a personal commentary so that if I cough in the middle, then you know, right? The Eastern Tropical Pacific has defied the global warming trend. There's been a debate about whether this observed trend is forced or natural. There is a natural mode called the interdecadal Pacific oscillation, which looks similar to what people are interpreting as trend, and whether IPO is the natural mode that is appearing in the analysis, or is there a combination or a superposition of the forced or the climate change signal because of increased greenhouse gases from human activity and so on. So this study shows that there are two patterns, one that oscillates along with the IPO and one that is emerging since the mid-1950s, herein called the Pacific Climate Change Pattern, or PCC pattern. Here we show that these have distinctive and distinguishable atmosphere-ocean signatures, while the IPO features a meridionally broad wedge-shaped SST pattern, as we will see. The PCC pattern is marked by a narrow equatorial cooling band. These different SST patterns are related to distinct wind-driven ocean dynamical processes. We further show that the recent trends during the satellite era are a combination of IPO and PCC. Our findings set a path to distinguish climate change signals from internal variability through the underlying dynamics of each. So you want to see if the natural mode, which has a similar multi-decadal time scale, the IPO, and the Pacific climate change signal, which obviously have to have a multi-decadal signal if you want to call it a change, and if they are distinct or if they are similar, if it is PCC is just a modulated version of IPO, or if PCC has distinct dynamics. Those are the key questions that they are answering here, and nice figures here to show right away what they mean. And this paper is unique because in the very first paragraph, no introduction, they jump right to the first figure with the analysis, and this is the figure. Had ISST trend 1980 to 2022, which has been looked at very extensively, talking about how the East Pacific is cooling, whether that means there is some kind of a thermostat effect because East Pacific cooling puts more heat into the ocean, which will damp the global warming and so on. And then there is the issue of whether this looks like a La Nina or it's a distinct mechanism altogether. And if you do longer term trend from 1958 to 2022, you can see that this cooling now looks much more damped, even though it is distinct from the west, which is still warming here, and the other details are there, what the Pacific and the Atlantic Ocean are doing, and there is a lot of literature on what these warmings do to the heat uptake in the Pacific itself, but here we'll focus on the tropical Pacific signature. So here is the equatorial Pacific SST evolution. If you look at a longer term period of the from the Industrial Revolution to about 2020 or so that they are studying here, you can see that cold tongue has remained relatively flat with some kind of a weak multi-decadal variability, let's say, whereas the warm pool took off since about the 1970s, and there's been a debate about whether there was a regime shift or whether there was really a warming trend, and whether there was a pause in the period after 1998 and so on and so forth. But West Pacific basically has shown a strong warming signal. If you do pattern correlation with tropical Pacific trend over 1980 to 2022 between different products, which is always key to look at, because there are data issues, especially when you go back in time in terms of the coverage. There's good coverage here because of trade between them here, but it can be very tricky here. So you convince yourself that the different products are doing fine, so the signal they are interpreting is quite robust, and then pattern correlation with tropical Pacific trend over 1958 to 2022, so slightly longer period, and you can see that there are some issues between the different products here, but they emerged out of this in the recent decades, let's say after 1990, so 1890, 2000 or so. Okay, so recurrent and emerging sea surface temperature SST trend patterns in the tropical Pacific. SST trend in degrees C per decade based on HALA SST during 1980 to 2022 and 1958 to 2022 here, and of course always as usual dotted regions are statistically significant. And 15-year running mean is shown here as well, which I already mentioned, and these are averaged over 5 south, 5 north, which is critical whether you are looking at the deep tropical Pacific, which is the region of interest in terms of the Walker cell, the coupled dynamics here between SST gradient, thermocline winds, and so on and so forth, right? So the SST anomalies were calculated relative to the climatology of the first 50 years. Such details matter, but let me skip this and look ahead to the next period. So here, next panel. Shading and D indicates pattern correlations of 43-year SST trends in the tropical Pacific region with interdecadal IPO pattern based on HALA SST, similar to D, but the 65-year SST trend with the trend during 1958 to 2022. Arrows labeled P1, so that's the 1870 to 1912 period, P2, which is from 1914 to 1956, and P3, which is 1942 to 1984, indicate the periods with the strongest positive and negative correlations in D, and P4 over 1970 to here goes my throat, 1870 to 1934, with the strongest negative correlation as shown here in E. Okay, so basically they are still trying to look at IPO, trends, and then emerging climate signal based on which period you look at, and you have to make sure that these results are robust across multiple products. Why are there multiple products? It's a different issue, but everybody reprocesses, combines past data in their own way. Let's not go into that. What are the results? I will just be brief here. Recurrent IPO pattern and emerging pattern related to the Pacific climate change. So I'm just reading the front part of this section. The SST trend pattern after satellite data become available, so 1980 to 2022, is often used as the observational reference for assessing climate model simulations of the forced response, which means due to greenhouse gas increases. This SST trend pattern is characterized by meridionally broad negative anomalies in the tropical Pacific. So this is what we are talking about. Particularly south of the equator, and positive anomalies in the northwestern and southwestern Pacific, which is like an IPO. If this trend is the positive to negative phase transition of the IPO, then it should appear in earlier historical periods, given that the IPO has experienced several phase transitions from 1870 to 2022. It's a natural mode of variability with a period that has made multiple phase changes. In figure 1D, we show that pattern correlation of the short-term trend during 1980 to 2022 with the tropical Pacific SST trend across all time spans of 43 years in the observational record. So 1979 to 2021, 78 to 2020, and so on, and also 1870 to 1912. Over the 30 south, 30 north, 120 east, 270 west, so basically the tropical, subtropical Pacific. The pattern correlations range from -0.8 to 1, demonstrating an oscillatory behavior matching the IPO's phase transitions over the last century. Again, a lot of these things are shown in supplementary figures. Analysis for the whole Pacific, 60 south, 60 north, and the zonal width of, or the equatorial Pacific, 10 south, 10 north, and the zonal width yield similar conclusion. And then there is some further discussion there that you can go and read. Jumping ahead, is there a distinct ocean dynamics for the IPO and the PCC? So you can say change signal has emerged, but is the change signal distinct in its processes, or is it just a modulation of the IPO? Closed Weakness feedback loop requires changes in the surface wind stress, the subsurface thermocline depth to accompany the SST variations. Weakness feedback is basically where let's say the winds change, the upwelling changes, eastern Pacific SSTs change, SST gradient changes, pressure gradient changes, winds change, upwelling changes further, thermocline changes further, so you have a positive feedback loop which works very well during an ENSO. In figure 3, we show that a recent short-term dipole-like pattern of the thermocline depth that recurs historically. In contrast, the emerging PCC SST trend pattern is accompanied by an overall shoaling throughout the tropical Pacific. So during ENSO you have the east-west oscillation, whereas the PCC trend is showing an overall shallowing of the zonal extent of the thermocline. Also, the recurring surface wind stress pattern in the equatorial Pacific features a broad strengthening of the zonal wind stress across the basin, which is consistent with the strengthening Walker cell and the Weakness feedback at that lower times frequencies, while the PCC wind stress trend pattern in the equatorial Pacific displays a dipole structure with strengthened wind stress in the central Pacific and weakened wind stress in the eastern Pacific. So trade winds versus the central Pacific. We also examined the variability of the surface wind stress and the subsurface thermocline depth that are directly linked to the IPO, which is shown in the supplemental. These IPO related patterns with dipole-like thermocline variability and same signed wind stress variability in the tropical Pacific bear close resemblance to the short-term trends, which is also shown. This supports the argument that the short-term trends over the span of approximately an IPO cycle predominantly reflect the internal variability of the IPO manifests across the tropical Pacific upper ocean and the atmosphere. So basically you have to be very clever about using IPO timescale to look at patterns. If you use only 1980 to 2022 and keep on concluding something, and that is basically a very strong combination of IPO and PCC, and you have to be careful what you claim, right? That's the main point. So here are the figures. Oops, figure 3, did I miss? Yeah, I jumped the discussion of figure 2, so let's look at this. So these are 43-year trend distribution for pattern correlation. So pattern correlation is shown here from minus to plus, and these are basically the range time periods going from 1912 So that's the end of the year trend out to 2020 or so. 65-year, it's 2020, I shouldn't say or so. 65-year trend distribution for pattern correlation. You can see there is a shift in the pattern correlation now. Negative here, and then bit of a negative positive, and then you are into positive here, right? So these are showing different periods, and we'll see the caption in a minute. Zonal SST gradient trend and the IPO contribution to that. So IPO contribution to 43-year trend shown in this dashed red line, and 65-year trend shown here in the bluish line, which stays positive after this period here. And the IPO contributions to the 65-year trend. So 43-year trend, 65-year trend, basically the IPO contribution doesn't go away, but the argument here is that the PCC clearly emerges distinct from the IPO after 1950. So this is the SST trend computed for 1970 to 2012 with near zero IPO contribution. So now you can see that the east-west contrast is still there, and the meridional pattern is still there on this side, but here the meridional loading of the negative pattern is quite different. So when this happens, different periods yield different results in this critical zone where Bjerkman's feedback can act strongly. Then you have to be very careful about what is IPO, the internal variability, and what is the anthropogenic trend or the forced trend, right? Quantification of internally generated and emerging Pacific climate change sea surface temperature trends shown here. Histogram of pattern correlations of 43-year SST trend patterns over the tropical Pacific in the historical period, with that during 1980 to 2022. So that you can look at the shorter period with patterns over the longer period to see how the IPO and PCC are mixing and when the PCC emerges. That's clear here, and especially clear here when you take 65 years. B is similar to A, but for the 65-year trend. C is quantification of the interdecadal Pacific oscillation contribution to the trend of the zonal SST gradient in the Pacific, and they are described in the methods on how that is done. The red solid line indicates the 43-year trend, and as I mentioned, the details of the 43-year trend in the red line, the 65-year trend in the blue solid line, contributions from IPO to the two in the dashed lines in red and blue. Okay. D is the 43-year SST trend in the 1970 to 2012 period with near zero IPO contribution. So that means basically the cooling here and the broader pattern here is the emerging PCC pattern which superimposes on IPO. So now they are acting together. So this is a complicated figure which has a longer caption, so I separated the caption. ORAS-5 is an ocean reanalysis product, because satellites don't give you thermocline for the longer period anyways, and many of these reanalysis products also can vary in their time periods. Nonetheless, thermocline trend over 1980 to 2022, shallowing here, and there is some signal here, deepening here, and some signal here. ORAS-5 thermocline trend for the longer period 1958 to 2022, can see the entire tropical Pacific seems to be shallowing or at least not deepening on this side. And if you look at wind stress and SSH trends, we are talking about the basin-wide trends being similar versus trends in the eastern versus central period. So this is what they call the dipole response and the basin-wide response. So those are the pattern correlations again with the trend over 1980 to 2022 from different reanalysis products, SODA, ORAS-5, and looking at winds and sea surface heights. Sea surface height is generally a indicator of the thermocline depth as well. Pattern correlation with the tropical Pacific trend for 1958 to 2022, and you can see here SODA is used for thermocline depth, SSH, and zonal wind stress, and now you can see much more of a trend versus an oscillation or a multi-decadal variability here. So now with that in mind, recurrent and emerging signals in the thermocline depth, surface wind stress and surface height, sea surface height, the thermocline depth trend in meters per decade based on ORAS-5 subsurface temperature during 1980 to 2022 and 1958 to 2022, again to separate IPO versus PCC. The surface wind stress vectors and SSH 1980 to 2022 and 58 to 2022 and so on. So pattern correlations of the 43-year trend pattern in the historical period for the thermocline depth that we already saw and SSH. So SSH and thermocline depth and the zonal wind stress are all shown together. Sorry. So there is no commentary here other than just describing what is shown. So you do different periods to again separate the real climate change signal versus the internal variability because they are superposed on each other. So wind-driven SSH trend 1980 to 2022. So what is the contribution of the heat? You can think of SSH also as heat content. You can see that sea surface height related to wind stress, wind-driven SSH over 1980 to 2022, high correlation, and it's dominated over these regions, and we are not going to do this worry too much about this, but they look at different averages in the meridional direction as well. And this is wind-driven SSH trend if you go for a longer period of 1958 to 2022. Correlation is still very high at 0.72, and here it is 0.87, but the pattern now highlights a different region and the sign is different as well. Positive, negative here, positive, negative here. Okay, so there is a slight change. And wind effect for 1980 to 2022 versus the longer period. What are they talking about? Wind-driven sea surface height change for decadal variability and climate change. So shorter period and longer period. Wind stress driven SSH trend in meters per day during 1980 to 2022 and 1958 to 2022 based on some equation that's in the methods you can look up. The pattern correlations between the wind stress driven and observed SSH trend pattern over the region of 20 south, 20 north and the zonal extent of the Pacific are displayed. Wind stress effect in meters per decade at each grid point, computed with this formula. 1980 to 2022 and 58 to 2022. So what is the wind in terms of the heaving of the thermocline or the SSH versus global warming and heat accumulation in the ocean? So there are two components. You can think of dynamics and thermodynamics in the atmosphere, circulation change and moisture change, precipitation change versus the ocean response where wind distribution, wind trends can change the upper level structure, and the warming in the atmosphere also affects the heat content in the ocean, right? So that's what they are doing. Another long figure here. Zonal current trends, so meridional structure for different periods. These are just details showing that there is a distinct dynamics of the PCC versus the IPO. So PCC is really independent of the IPO, and a real climate change signal has emerged because it's a sensitive region with the east-west gradients, responses in SST gradient, pressure gradient, winds and ocean and positive feedbacks. You want to be sure that the Pacific climate change is picking different scales and mechanisms compared to IPO, which is a much broader natural variability or internal variability. So vertical current trends as well. Obviously you can see here the changes in the Bieknis feedback and the cooling and the feedbacks in the atmosphere in terms of wind and so on as well. And this is so ABCD and IPO related geostrophic current trend and emerging geostrophic zonal current trend. So obviously IPO, if depending on the phase of it that you are looking at, it has negative meters per second per decade trend, which means the south equatorial current and the westward push are stronger in the IPO related zonal currents in the ocean, which would favor an upwelling and cooling here, whereas the emerging geostrophic zonal trend current is positive, which means it is actually consistent with the wind dipole that we looked at, and the basically like a opposite direction of IPO. So one is trying to increase the upwelling and westward transport, the other one is actually decreasing it. IPO related Ekman pumping trend, so wind stress curl and the Ekman pumping are shown here, and emerging Ekman pumping trends, and you can see the dipole pattern here versus more zonally uniform pattern here. Associated with this, there will be subtropical cells as well that I will not go into. So I will not bother to read this long caption again, because they are basically using different periods and different products. I can see ORAS 5, so everything is being done from the same product, but then that doesn't matter. It's basically consistent with what we are saying. So here ocean dynamics for the central to eastern Pacific cooling linked to the interdecadal Pacific oscillation and the Pacific climate change. So they are separating the two, and you are looking here at the warming rate degrees C per month. So that is IPO related central to eastern SST change, and IPO was cooling in the total, and you are splitting it into different terms. So ocean currents UATC, VATC, WATC, temperature gradient change UCTA, VCTA, WCTA, and non-linear terms like UATA. So you can go and look at the equations on how they split it, but just focus on the different terms and their contributions. And the main point I would take from this is that the emerging emerging central to eastern Pacific SST change has a different dynamic that is distinct from the IPO. So it's just emphasizing the same point. So you can see the sum is here negative, also negative here, so they are going in the same direction, but the contributions from different terms, linear and non-linear terms, are different, including vertical terms and so on. There are always some uncertainties when you do this from the reanalysis products, because if you know what reanalysis are, basically they are shoving data into a model that's being integrated forward, and introducing data can create some inconsistencies or dynamic pulls. The model data pull the dynamic ocean dynamics in certain directions, but you can make sure that the residual terms are looked at, and so on and so forth. So you have to look up the details if you want to follow up on what these terms mean. Let's just jump to the discussion, because this is getting a bit long. So I'll read the whole thing just to make sure we get the most salient points, since I'm being a little lazy on the figures. Much recent work focused on whether equatorial Pacific cooling over the past decades is driven by anthropogenic effects or arises from internally generated climate variability like the IPO. A definitive anthropogenic link to the recent trends would allow us to reliably predict a cooler tropical Pacific, as the tropical Pacific Ocean is known to be a climatic pacemaker for the global warming. For at least the near surface, this would mitigate global warming via the ocean heat uptake and low-level cloud feedbacks. So if East Pacific cools, atmosphere puts more heat into the upper ocean. Some of it gets released by El Niños, but some net uptake happens, and there is an atmospheric response in the clouds as well in terms of the stratus deck, let's say. Instead of the cyclic IPO dominates, if the cyclic IPO dominates the recent cooling, we may expect a strong warming when it reverses. So if you are having a cooling and it's just a natural variability, and suddenly the climate change emerges, then you may see very rapid warming with the release of heat from the ocean, and so on and so forth. I shouldn't say so on and so forth, related feedback processes in the system. In support of this, of the first possibility that it's not just IPO, we have identified an emerging climate change signal in the tropical Pacific across different observational data sets, and we call it the Pacific Climate Change, or PCC. The PCC has distinctive ocean atmosphere dynamics that differ from those associated with the IPO. We further demonstrate that the recent trends during the satellite era, which have been the focus of significant attention, result from a combination of IPO and PCC. The emerging PCC SST trend pattern features a narrow band of cooling in the eastern equatorial Pacific and warming elsewhere. This SST change is linked to thermocline shoaling. SSH decreases in the central to eastern Pacific. Thermocline shoals, sea surface height decreases as we expect. I have other podcasts on why this should happen, but where was I? Okay, we further demonstrate that the recent trends during the satellite era, which have been the focus of significant attention, result from a combination of IPO and PCC. The emerging PCC SST trend pattern features a narrow band of cooling in the eastern equatorial Pacific and warming elsewhere. This SST change is linked to the thermocline shoaling. SST and thermocline shoaling and SSH decreases. I'm fumbling this. In the central to eastern Pacific, and dipole-like changes in the zonal surface wind stress. In contrast, the recurrent IPO-driven SST trend pattern is characterized by a meridionally broader cooling in the eastern Pacific, zonal dipole-like thermocline SSH changes, and an overall strengthening of the tropical Pacific zonal wind stress. We have shown that these distinct ocean circulation changes are a response to different wind stress patterns. These oceanic responses account for surface cooling in the eastern Pacific, with the thermocline shoaling playing a dominant role in the PCC cooling, and enhanced zonal advection enhanced zonal advective cooling mainly driving the IPO related cooling. So you can cool by moving cold water away, bringing up more cold water, divergence, or can shallow the thermocline and just have processes, vertical processes, take care of the cooling and the warming patterns. While basic geophysical fluid dynamics proved sufficient to attribute the observed oceanic changes to surface wind stress, we have not addressed the origins of the wind stress patterns associated with the PCC and IPO. Right? New research is needed to elucidate the wind changes, but our leading hypothesis is as follows. It's a nice way to end the paper. In response to greenhouse gas forcings, temperature change in the upper troposphere are stronger than at the surface, which is shown in a supplementary figure, and this increases atmospheric static stability. So the lapse rate changes in a way to make it harder to convect, let's say. Consequently, the initial SST and subsurface wind responses to rising GHGs may not be amplified as efficiently via Beckness feedback as is that for the internal modes on annual to decadal timescales. So there is a response to the warming and the stability changes versus the internal variability, and they are different. Given the differences in the thermocline and ocean current patterns associated with the PCC and the IPO, the coupled feedbacks related to ocean dynamics are also expected to differ, potentially contributing to distinct climate pattern formations for decadal variability and climate change. Additionally, climate variations outside of the tropical Pacific may influence the tropical Pacific trade winds, obviously. Further, it has been argued that pronounced decadal to multi-decadal SST variability in the Atlantic Ocean is also dominated by the response to the same external forcing that the tropical Pacific Ocean encounters. Perhaps the co-occurrence of these long-term trends in the different regions is not simply a direct response to rising GHGs, but is influenced by interbasin interactions in addition to that. More work is needed to disentangle causal relationships among the long-term changes in different basins and their interactions. Throughout this paper, we have taken for granted the widespread assumption that the IPO is an internal mode of climate system. However, while we work to distinguish between recurrent IPO-related decadal variability and the emerging PCC signal, we are open to the possibility that these two may have become coupled together by anthropogenic forcing. So, internal variability begins to get modulated by the anthropogenic forcing, and then the two may become harder to disentangle. They have much in common, of course: shoaling of the thermocline in the east, enhanced upwelling somewhere in the central to eastern equatorial Pacific, and an enhanced zonal SST gradient across the equatorial Pacific. It seems reasonable to postulate that if the response to radiative forcing is the emerging PCC pattern seen in here, then it could initiate coupled ocean-atmosphere feedbacks that favor a negative IPO state that also has an enhanced SST gradient, which means the IPO may become more persistent in its time scale. This might explain why the most recent IPO sinks This might explain why the most recent IPO swing has been extreme and robust. You can look it up in the supplemental. If so, this suggests that in nature, forcing is projecting onto natural modes of variability, while it's not clear whether climate models can reproduce this behavior. A new perspective on how internal variability interacts with climate change signal will be needed in future studies. And Richard has written papers already showing that the models are not capturing the Eastern Pacific cooling properly, and he's been working on this topic for a long time, several decades. So he's obviously studied this in great detail, and is an expert and tracks model performances just to make sure that what they are saying about the future is not too far off from reality. Okay, so let's leave it here. More than 35 minutes long, but it's a nice paper, it's a nice discussion, and hopefully it's helpful. And you obviously need to read the paper if you want more details. See ya! Okay, maybe I was a little too lazy with the thermocline dynamics. The equations are shown here, and this is covered in the next podcast, where the same group, I think it's a student, and Richard Seeger and Mark Kane are looking at the subsurface variability in the tropical Pacific to complement this study. And this is how they do the heat budget analysis. We talked about these terms here. Heat budget for each grid point in the subsurface ocean is temperature change, and you have a zonal and meridional advection terms together with vertical term, which is more complicated than just advection if you want to do the mixed layer budget separately. But if you are doing just the heat content and SSH, then it's okay. And then you have a residual term. So they write it as advection plus residual term. So residual term R for the subsurface ocean includes diffusive flux, sub-monthly and sub-grid scale processes, and errors due to data resolution and computation. So the reanalysis products typically don't close the budget, so you always end up with the residual term, and this is an issue even if you try to do it purely from data anyways, as Mike McFadden does in a lot of his papers. The advection terms can be further decomposed into UADTDXC, so that is written as UATC that we saw before, and UC partial dTdx, so UCTA plus UATA and VATC VATA. So climatology versus anomaly. So typically what you do is you want to see what term is the advection of anomalies by the mean current, of temperature anomalies by the mean currents, versus what is the advection of mean temperatures by the anomalous currents. So you have anomalous currents, temperature climatology, climatological currents, temperature anomalies, and for all zonal, meridional, vertical terms. I should have done that before, but we'll see you in the next podcast to look at more details of these processes for the tropical Pacific. Okay, see you.